How long have you been waiting there? Say something next time. So we're continuing along with threads. This is sections 4 through 6. These three sections of the chapter. And here are the chapter objectives one more time. So as we already know, a library provides an API for programmers. And thread libraries, user thread libraries will be implemented in user space. So no kernel mode code. Kernel threads will be implemented in a kernel level library with the code running in kernel mode through syscalls. So pthreads is a standard, which means that it specifies the API, but doesn't explicitly specify an implementation. So conceivably, there could be multiple implementations of pthreads offered by different groups. Right, and there could even be a slightly different behavior between the implementations, and as noted in the final bullet, pthreads is common in Unix operating systems, including Linux. So if you're going to write a program using the pthreads library, you need to include the header file for pthreads to bring in various definitions and function prototypes. The function that runs, or that a thread runs, should have this sort of a form. So it takes one parameter, which is a pointer to void, and the return type of the function should also be pointer to void. The name's immaterial. You could use any name you wanted. In this example, the thread ID, TID, corresponds to PID, the process ID, except of course this is for threads. Attribute is well, as it says, the attributes for the thread. So the settings. So examples of some of the attributes are scheduling policy and stack size. So this call is used to get the default attributes, and notice that the parameter here is being passed by address, so that the function can modify the parameter. Then this function creates the thread. The thread ID is returned. Again, note that this is being passed by address. The attributes are passed in, but again by address. The way this this argument here, which is a pointer, will be passed into the one parameter of the thread function, and this is the named thread function here. This is done in a general way. So this runner program here is expecting an integer value to be passed as a string, which then converts to an integer value through the a to I function. Again, this is a general mechanism. We can do whatever we would want, just so long as we fit it into the constraints that the thread function takes one parameter, which is pointer to void, and returns pointer to void. So this function creates the thread and starts it running, and then the main thread will wait here. Join corresponds to wait, and it'll wait for the thread with this thread ID to complete before it continues along. So here's the thread itself. It looks like it's just computing a sum, and then finally exits. So in this example, we're assuming that we've already created num threads, or 10 threads, through calls to create, and stored their thread IDs into this array, and then the main thread will join them all. So it'll block this for loop will cause it to block until every single one of the worker threads has completed. I'm going to skip this, skip this, skip this, skip this, and skip this. Tom, we already need to talk about all these skips. So the trend here is for more CPU cores per workstation. In order to take advantage of those cores, ideally we would want to partition a program into more and more threads. But of course, as the number of threads, and remember they're running in parallel, as the number of threads increase, testing and debugging decrease, probably in about an exponential way. So what can we do to help a programmer? Well, what comes to mind is to push the management of the threads down to the compilers and the runtime libraries, and perhaps even using those tools to find parallelism within our programs. So parallel programming is a topic for an entire course, but in one of your later projects, you'll get to practice with p-threads. There's not much that I want to say here. Thread pools are pre-existing threads available as a program needs them. These pools won't help with parallelizing a program. They're simply will help with the creation of threads. OpenMP is an API for parallelism. Note here this pragma, which is a hint to the compiler, says that this is a parallel for. So the next statement will be executed in parallel. Each thread will take one statement in the for loop, and note that the way this particular for loop is written, there's no dependencies between element a sub I and a sub I plus 1 or a sub I minus 1. Right? If you think about this for a while, all of these statements in the for loop can be executed independently. So there's no need for synchronization between the threads. Here in this example, this is a parallel region. I know that the region is defined by the braces here, and as commented, one instance of this printf will be run by each thread, and one thread will be created for each core in the system. I'll skip this and probably take grief from all the Apple fanboys out there. Skip this. So now we'll move on and talk about thread library design issues. So one question that a thread library designer would have to address is how fork behaves in a multi-threaded program. Does only the thread that invoked fork get duplicated, or do all of the threads get duplicated? And as pointed out, some Unixes have two versions of fork to cover both cases, and then when a thread execs another program, what happens? Are all of the threads exec, or just the one that is running, that actually runs the exec? Signals are a user-level abstraction of exceptions. Processes can send signals to each other. As noted, when a process starts up, there's a default handler for each signal, but a process or thread can install its own signal handler to override the default. And in this case, for a threaded program, the design decision is if a task receives a signal, is it is the signal delivered to all of the threads in the task, or just a single thread? Or even if there's there could be a special designation, such as a subset of the threads receive the signal, or a designated thread receives the signal. Threads can terminate each other. That's called cancellation. And the design decision there is if one thread cancels another thread, the target thread, does the target thread terminate immediately? That would be asynchronous cancellation. Or does it do it on a deferred basis, meaning that it can clean up after itself before it terminates? Why would we want the target thread to clean up after itself first? Well, it could be holding a lock, and if it terminated while holding the lock, that could cause the program to deadlock. It might have other resources, such as files that are open, that need to be closed before the thread terminates. So here are the possibilities in the pthread library. If the mode is off, the thread is immune to being canceled. Deferred means that it's given the opportunity to clean up before it cancels, and asynchronous recall means that it will be canceled, i.e. terminated immediately. I'm going to skip this slide, and I'll skip this slide. So that concludes chapter 4. Did you get a load of the bald spot on that guy who was speaking at the beginning of this? Wow.